Welcome to This Explainer. Today, we're diving into what is basically a massive detective story right in the world of data science. We're going to uncover hidden structures and invisible patterns using a seriously brilliant tool, the k-means clustering algorithm. If you have ever wondered how computers can find perfect order in absolute chaos without any human guidance whatsoever, you are in exactly the right place. Okay, let's set the scene for this mystery. Imagine you're staring at just a massive, sprawling sea of data. You've got thousands, maybe millions of data points in front of you, but you have absolutely no labels telling you what any of it means. There are no categories, no tags, nothing. How on earth do you group things together when you literally don't know what you're looking for?
Well, this exact mystery is the whole idea behind an unsupervised learning problem. In traditional supervised learning, we give the computer an answer key, what data scientists call while labels, so it can learn by example. But in an unsupervised problem, our algorithm is flying completely blind. We hand it a training set of raw data, but absolutely no predefined answers to learn from. It has to figure out the underlying structure on its own.
So that brings us to our actual mission with the k-means algorithm. We need to take this chaotic, totally unlabeled data and wrangle it into a specific number of cohesive, organized groups. We simply refer to that target number as k, meaning if we want to find 3 groups, k equals 3. If we want 5 groups, k equals 5. The goal is to hunt down these k distinct clusters hiding right there in the noise.
To pull this off, we need to bring in our lead detectives. In data science, these are called cluster centroids. But honestly, just think of these centroids as the algorithm's best ongoing guesses for where the exact mathematical center of each of our k groups is located. They're going to be doing all the heavy lifting as we crack this case.
To really visualize what's going on, picture your raw training examples, that unlabeled data, as just a bunch of scattered dots spread all over a graph. And to tell our detectives apart from the clues, we'll represent our cluster centroids as bold crosses moving around among those dots. So dots are the raw data, and crosses are our current guesses for the group centers.
The absolute first step of the algorithm is beautifully simple. We just randomly drop our k-centroid crosses right into the mix of scattered dots. A super common way to do this is to literally pick k random dots from our data and drop the crosses directly on top of them. At this point, it's just a total wild guess. The crosses are basically saying, all right, I guess the center of a group is right here. Now here is where it gets really interesting. The core engine of k-means, right after that random guess, is a continuous, repeating, 2-step loop. It's just an assign phase and a move phase. Literally everything the algorithm does from here on out boils down to repeating these 2 basic actions over and over again. Let's break down step A, the assign phase. The algorithm looks at every single dot, one by one. It calculates the distance between that dot and all of our crosses, and then boom, it logically paints the dot the exact same color as the cross it is physically closest to. It's basically assigning loyalty. Every dot looks around, finds the nearest cross, and says, yep, I belong to you.
Then we instantly jump to step B, the move phase. Now that the dots have picked their teams, the crosses look at their new flock of followers. The algorithm literally picks up each cross and shifts it right to the mathematical average, the exact mean position of all its newly painted dots. The cross moves so it's standing perfectly in the center of its new group.
And then the magic happens. The algorithm just rhythmically repeats the whole thing. Because the cross is moved, the distance is changed, right? So we loop back to step A, reevaluate the dots and repaint them based on the new closest cross. Then step B, move the crosses to the center of their new groups again. Assign, move, assign, move. It keeps this rhythm going until the crosses completely stop shifting. That final resting state is a perfect balance we call convergence. But hey, you might be wondering, is this algorithmic dance actually guaranteed to stop? I mean, could it just bounce around forever in some infinite loop, constantly trading dots and shifting crosses back and forth?
Well, it is absolutely guaranteed to stop, and we can mathematically prove it using something called the distortion function, labeled as j. Think of this j function as the algorithm's score of badness. It measures the sum of the squared distances between every single dot and the cross it's currently assigned to. So the further away the dots are from their crosses, the higher and worse that j score is.
So here is the crucial takeaway. Underneath all that visual back and forth of dots and crosses, k-means is actually performing a very strict mathematical operation called coordinate descent. Every single action it takes is mathematically forcing that j-score, our score of badness to shrink.
And this strict alternating behavior is exactly what builds our proof of convergence. First, we lock the crosses in place to update the dots, which lowers J. Then, we lock the dots in place and move the crosses to the perfect center, which lowers J again. Because of this strict alternation, the J score must monotonically decrease. It literally can never go up, and since it can't go down infinitely, it eventually hits a hard mathematical floor, forcing the algorithm to stop. Boom!
However, every brilliant detective has the blind spot. For the k-means algorithm, its absolute kryptonite is the fact that this distortion function J is what we call a non-convex function. Sure, the score is guaranteed to go down, but a non-convex function means the mathematical landscape is bumpy. It has a bunch of different valleys you could get stuck in, rather than just one single perfect bottom.
This bumpy, non-convex shape means our algorithm is super vulnerable to something called local optima. Basically, depending entirely on where we drop those random crosses at the very beginning, the algorithm might hit the bottom of a nearby valley and just get permanently trapped in a clustering that's, well, just okay. It thinks it solved the mystery perfectly, but a way better absolute best grouping actually exists just over the hill, and it completely missed it.
So, how do we escape this trap? We don't rewrite the math. We just use a really clever and incredibly common workaround. We run the entire k-means algorithm a bunch of times from scratch. Every single time we run it, we use completely different random starting positions for our crosses. By mixing up the starting lines, we explore different valleys in that non-convex landscape. Once we've run it, say 50 or 100 times, we just look at the pile of final results and pick the one with the absolute lowest distortion score. Simple as that. By turning all this complex coordinate descent math into a highly visual, almost gamified turf war, k-means gives us a brilliant way to solve unsupervised learning. It lets us step into a massive sea of unknown information and literally watch the structure reveal itself. It really makes you think, doesn't it? What kind of invisible structures and wild relationships are hiding within your own unlabeled data, just waiting for the right algorithm to bring them to light? Thanks for hanging out with me for this explainer, and keep questioning the data around you.